All right. Good morning, Trisha, Michael, John, Christian, and Prince. Today is a nice day because this would be the last meeting for Math 155 before we go on to our almost 2 week break, right? So meron kasi tayong reading break next week. Tama no? Next ano na yun? Next week na yun. And then after that, we're gonna have the Holy Week, which is another avenue for us to rest. Okay. I'm thinking of calling Holy Tuesday a holiday for the class. So para madagdagan yung bakasyon nyo. So wag na tayong mag-meet on Holy Tuesday. But I hope to finish today unit number 2. In case I don't, so ibibigay ko na lang sa inyo na watching assignment. Parang pangit pakinggan ng watching assignment. No? Bakit gumagana siya sa reading assignment pero sa watching assignment hindi? But I'll uh, I'll give you the remainder of the unit as a watching assignment kasi na-lecture ko na naman to last semester. So you can watch the video instead of coming to class on Holy Tuesday. So pwede nyo siyang gawin during your free time all over the stretch of the 2 weeks. All right? Para lang may closure na tayo sa unit number 2. And then when we go back fresh from our contemplation during the Holy Week, we can start talking about unit number 3, which is basically about limits of functions. All right. So, ano pa nga ba? I think that's it. We won't have homework for the duration of the break para lang matodo natin yung ating pagpapahinga. But before we start, I want to share to you this nice GIF that I found. So it's about celebrating the little victories. And I think this is something that we often overlook. Na we always feel that we are not doing so much or we feel guilty na masyado tayong feeling natin, masyado tayong nagre-relax o masyadong hindi tayo nagpapakapagod masyado, right? But I guess it is really worthwhile to give ourselves a pat in the back even if we accomplish just a little thing. Because those little things, when you sum them up, it will become significant. Parang integral lang yan. Yung mga maliliit na bagay na ginagawa natin day in and day out, hour in and hour out, that when compressed together will give us something of value, something of significance. And oftentimes, other people will not be able to recognize or appreciate that kasi minsan tayo lang yung nakakaalam ng mga maliliit na bagay na ginagawa natin that contributes to our success. Yung ibang tao nakikita lang nila yung success natin, yung finished product, but they don't see the struggles within, the little victories we gain day by day. So it's up to ourselves to just celebrate this and give ourselves a sense of fulfillment. All right? Kaya nga laging gusto kong hinahati yung mga goals ko sa maliliit na piraso para meron akong reason to celebrate. Sometimes these are excuses to reward myself. So maisip ko, nakapag-check ako ng problem set tonight, I can probably reward myself with a good cup of coffee or my favorite pork floss soft roll or pwede akong umorder sa Lazada, right? So yeah, that's my little thought for today. So regular programming again. So last time we started talking about the big consequences of the completeness axiom. We talk about the monotone convergence theorem at saka yung I think nagtapos tayo sa nested interval property. Tama nga ba? Yun lang yung dalawa. Yeah, monotone convergence theorem and then the nested interval property. And I think we also went over the proof of the nested interval property last time. And the main ingredient or the main tool that we used in order to prove the nested interval property ay yung MCT. Tapos yung MCT, I think yung main ingredient natin sa kanya ay LUB property. So that shows to us the interconnectedness of these theorems. And in fact, nasabi ko na nga, kasama sila dun sa multiverse ng completeness axiom. So in another textbook, some author might have used the nested interval property as the completeness axiom instead. Okay? So ngayon titingnan pa natin, I hope we can discuss 3 other big theorems in real analysis. Actually, hindi lang about sequences, pero in real analysis in general, because again, all of real analysis is founded on the completeness axiom. All right. So the first one is the Bolzano-Weierstrass Theorem. Okay. So may typo rito. Lagi ko nakakalimutan i-correct. It's the Bolzano-Weierstrass Theorem, and it tells us that every bounded sequence contains a convergent subsequence. So parang ano to, ito yung consolation prize para sa mga bounded sequences. Kasi sabi natin in a counter example last time, when you have a bounded sequence, it will not necessarily converge. Actually, we need to add another property to boundedness to guarantee convergence. At ang nakita natin, isang posibleng idagdag natin para mag-guarantee yung convergence ay pagiging monotonic. Alright? Pero on itself, ano yung uh, pinaka malaki or pinaka magandang property na pwede nating attribute to bounded sequences insofar as convergence is concerned? Yun yung binibigay sa atin ng Bolzano-Weierstrass. Ang sabi ni Bolzano at ni Weierstrass, pag meron kang bounded sequence, sure tayo na yung sequence na yon ay merong isang convergent subsequence. All right? And the proof is a constructive proof, right? So ito yung, kasi kung titingnan niyo yung statement ng theorem, ano to, it's an assertion of the existence of something. It's telling us na basta meron kang bounded sequence, laging magkakaroon ng convergent subsequence yung bounded sequence na yon. So one way to prove this is via construction. Tinasabi ng theorem, meron nag-exist. So why not let's construct that sequence or that convergent subsequence? And that's what we're going to do in this kind of a long proof. Okay, kaya sinulat ko na siya dyan. Hindi ko na siya tinakpan kasi mahabang sulatin. Let's just dissect the proof line by line and understand how it was done. Okay, but keep in mind that we are here in up to a construction of such a convergent subsequence. Okay. So ang assumption natin, meron tayong bounded sequence, all right? And by definition of boundedness, we can always find a positive real number m such that the absolute value of all of the terms will be less than or equal to capital M. Or in other words, we can find a lower and upper bound for the terms in the sequence, all right? So itong statement na to, kasama na dyan yung lower bound saka upper bound because this absolute value inequality can be stretched into a continued inequality. That is, negative m is less than or equal to an less than or equal to m. Right? So ngayon, ang goal natin, sabi ko nga, mag-construct ng isang convergent subsequence and we can divide the proof, we can divide the construction into two parts. Yung unang part ay, kunwari, yung sequence, meron siyang infinitely many repeating terms. All right? So, example nung mga sequence na may infinitely many repeating terms, halimbawa, yung negative 1 to the power n. All right? So, if you will look at the sequence, alam natin, nag-alternate lang yan na negative 1 at saka 1. All right? So, yung negative 1 acts as a term of the sequence infinitely many number of times. So, super daming beses nag-appear si negative 1 doon sa sequence. Ganun din si 1. So, ibig sabihin, kung meron kang isang sequence na merong isang number na nag-act as a term infinitely many number of times, then I can just get the subsequence consisting of that constant term. All right? So, halimbawa, dito sa negative 1 to the power n, kunin ko yung subsequence na ang laman lamang ay puro ones. And we all know that the sequence of constant terms will be convergent. And then actually, that is enough proof for the convergent subsequence as claimed by Bolzano-Weierstrass Theorem. Okay? So ito yung madaling part ng proof. So pag may nakita ka ng infinitely paulit-ulit na terms dun sa sequence, edi siya yung kunin mong subsequence. Sure tayo na siya ay convergent. Right? Now, the more challenging part of the proof is kunwari, walang infinitely many repeating terms. Hindi gagana yung pandaraya natin dun sa construction. Oh, by the way, that worked, all right? Because the theorem is just a claim of existence. Sabi lang ng theorem, meron. So pag nakapagbigay ka ng isang example, ibig sabihin, na-prove mo na yung theorem. All right? So case 1 is easy. Meron tayong pandarayang ginawa. Pero hindi naman laging yun yung nangyayari. Halimbawa, meron kang sequence na 1 over n. Wala diyang nauulit na term. Yan ay 1, 1/2, 1/3, 1/4, 1/5, and so on. And none of the terms repeat, even twice. All right? So, ibig sabihin, X na. Hindi na siya papasok dun sa case number 1. So so that means we need to write a proof for this particular scenario. Okay? So yun yung nasa case 2 nung proof. Tingnan natin kung paano siya ginawa. And meron bang nag-175 dito? I think Michael nag-175 ka, no? Si John Christian ba? So dami kong estudyante, hindi ko masyadong matandaan, no? Pero parang familiar itong magiging proof ng pag walang infinitely many repeating terms. Yeah, tama. Si John Christian din nag-175. So parang kamukha to ng bisection method. Alright? Medyo kamukha lang. Hawig lang yung process, right? So ang gagawin natin, alam natin bounded yung sequence. So that means we can say na yung A sub n, by our assumption above, is a subset of negative m to m, a closed interval. Alright? Kasi nga yung absolute value ng an ay mas maliit or equal kay m. So yung sequence ay napapaloob sa isang closed interval, specifically negative m to m. Tatawagin ko yung I1. Tapos, bakit tinawag yung I1? Kasi gagamitin ko yung nested interval property. So ang gagawin ko sa second step, alright, hahatiin ko yung I1 sa dalawang parts, dalawang equal parts. So kung meron ako ditong negative m, meron akong positive m, hatiin ko to sa dalawang subintervals, negative m to 0 at saka 0, m. So tapos, tatawagin kong si I2 kung sino dun sa dalawang intervals na yon ang nagko-contain ng infinitely many terms dun sa sequence. Alright? Now, is that really possible? Well, from negative m to m, nandyan lahat ng mga a sub n. So there would be infinitely many terms in the sequence in the interval negative m to m. Not necessarily iba-iba sila, right? Pero marami dyan mga a sub n's for infinitely many number of subscripts n's. Alright? Tapos hatiin ko siya sa dalawa. Pipiliin ko to be I2 kung sino dun sa dalawang subintervals negative m to 0 at 0 to m yung naglalaman ng infinitely many a sub n's. And I am sure that at least one of these two intervals will consist of infinitely many a sub n's. Alright? Kasi hindi pwedeng pareha sila finite lamang yung dami ng a sub n's na laman nila. Kasi kung finite lang yung laman nito, finite lang din yung laman nito, di meron lang finite number of terms from negative m to m, which is impossible kasi nga infinitely many yung terms ng sequence. Meron tayong infinitely many a sub n's. So we're sure that at least one of these two intervals will consist of infinitely many a sub n's. All right? So yun yung tatawagin nating I2. Halimbawa, si 0 to m, yung matatawag nating I2. All right? So si 0 to m, meron siyang infinitely many number of terms. Tapos ang gagawin ko, ulitin ko yung proseso. Hatiin ko to sa dalawa. 0 to m over 2 and from m over 2 to m. And then since I2 contains infinitely many number of terms, then the two subintervals we mentioned will contain, or at least one of them, will contain infinitely many terms in the sequence. Tapos yun yung tatawagin kong I3. So, halimbawa, ang I3 natin ay, halimbawa, si 0 to m over 2. And let's call that our I3. And then this process goes on forever, all right? Paulit-ulitin ko yung gagawin, mahati siya ng mahati into several subintervals. And then up to the last interval, or even if we are on the 1,000th interval, that interval is guaranteed to have infinitely many terms in the sequence. So hindi tayo mauubusan ng elements, hindi tayo mauubusan ng interval na merong infinitely many number of terms. Okay? And then we can get a sequence of intervals, I1, I2, I3, and I4. Now, let's observe what are the properties of these intervals. Well, remember yung construction natin, paliit ng paliit yung mga sets na kino-consider natin because their lengths would be half of the length of the preceding interval. And actually, that is a part of the preceding interval. I mean, I1 is a superset of I2, I2 is a superset of I3, and so on. And that's via the construction we did. All right? Tapos another observation, yung length nung pang n na interval ay kalahati. Ano nga ba? Ang length nung pang n na interval ay kalahati nung sumunod na interval. Tama ba to? I1 ay equal sa half ng I2. Parang baligtad. Kasi ang length ni I1 ang length ni I2 ay kalahati ng length ni I1. So that means this should have been a minus. Tama ba? Do you agree with me, guys? Dapat minus to. Oops. Kasi 'di ba yung length ni I1 yung length ni I2 ay kalahati ni I1. Yung length ni I2 ang length ni I3 ay kalahati ng length ni I2, right? So this should have been a minus. Let me just mark this for correction. Okay. All right. So and then another observation, again by construction we know that each of the INs will contain infinitely many A sub n's. So that's fine. And then makikita ko, nested yung mga intervals. An interval is contained in the previous interval. So I can use the nested interval property here. But before I appeal to that, I'll take advantage of part B. All right? Alam ko ng length ng nth interval, tawagin natin siyang Cn to Dn, right? This would be the length of In. Tama na pala siya dito. Siya ay 1/2 ng length ng previous interval. Tapos, ito ay 1/4 or 1 to the 2 squared ng I sub n minus 2. Alright? Kasi kakalahatiin ko uli siya. Or probably gawin natin step by step. So this would be 1/2 times yung length ng I sub n minus 1 ay kalahati ng length ng I sub n minus 2. Alright? And then, if you go on, this would be 1/2 squared times 1/2 length ng I sub n minus 3. So basically, ang nangyayari in general, we will have the nth interval will have length what? 1/2 to the power n minus 1 times length ng I sub what? I sub 1. Tama ba? Kasi yung I sub 1, pwede kong isulat na n minus 1. Alright? Kasi kung makikita nyo, ang length ni I2 na multiply ng 2 squared sa denominator. Yung length ni I3 may divisor na 2 to the third. Now, if you continue the process, you will see that this length will be 1/2 to the power 4 length ni I sub n minus 4. So yung subtrahend dito sa subscript ng interval will serve as the numerator ng divisor na 2. Alright? So if I will do this process down to the length of I1, so si I1 pwede kong isulat as I sub n minus 1. Alright? Tapos by the pattern we observed, this subtrahend will be the power in the denominator 2. Alright? Ano ang haba ni I1? So remember, this is just length of I1. Pero ang haba ni I1, si I1 ay from negative m to m. So that's going to be 2 times m. Tama, no? Siya si I1. So that means what? So this would be 2/2 to the n minus 1 times m. Tapos, pwede kong tanggalin yung 2. So, ano mangyari? 2 to the power n lang, no? Tama ba? 2 to the 1 minus n minus 1. That's 2 to the 2 minus n. N minus 2. Kasi mababawasan yung denominator ng isang power na 2. So, tama ba? Tama ba yung adjustment ko? So, yung length ng nth interval will be m over 2 to the power n minus 2. But when n becomes very, very large, the denominator here will be very, very large. Kasi ano siya, m over 2 to the power n minus 2, n goes to infinity. So this guy, the denominator, will become a very large number. We have a constant divided by a very large number. So the length of the interval will approach 0. Okay? So, ano ngayon kung yung length ng nth interval ay papunta kay 0 habang lumalaki yung subscript? So that means we can apply yung naka-moreover dun sa statement natin ng nested interval property that the intersection of the intervals in our nested family is just a singleton and it will contain A, right? But what is A? A is the limit of D of D sub n and the limit of C sub n. All right? Tapos nakita natin from the proof nung nested interval property, siya yung supremum ng mga A sub n's or mga C sub n's in this case. Tapos siya yung infimum ng mga D sub n's. All right? So this is basically siya equal kay A. And I claim that A is the limit of the subsequence. All right? So, di ba, ang promise natin dito, ang gusto natin mag-construct ng subsequence. Sir, puro analysis pa yan. Nasa na yung kailangan natin na subsequence? So, yung subsequence, ganito ko siya i-construct. Pipili ako ng isang element ni I1. Okay? So, si I1 ay negative M to M. Pipili ako ng isa sa kanila. So, pipiliin ko siya ay pipili ako. Halimbawa, siya si A sub N sub 1. Okay? Tapos kay I2, pipili ako ng isang element, all right, whose subscript is greater than the first element that we have chosen because we want to show that there is a convergent subsequence, all right? So sa I1, pipili ako ng A sub n sub 1. Tapos kay I2, pipili ako ng A sub n sub 2. The only requirement is that n sub 1 must be less than n sub 2 kasi nga dapat mapreserve ko yung order ng sequence. Tapos mula kay I3, bubunot ako dyan ng isang element nung isa sa mga A sub n's. Tapos siya yung i-assign ko na n sub 3. Alright? But again, the requirement is that A sub n sub 3 should be greater than both n sub 1 and n sub 2. Kasi nga, ang usapan, subsequence dapat yung bubuuin natin. So yung mga subscript dito sa subsequence na binubuo natin ay dapat nagpa-follow dun sa restriction and definition of subsequence. And I am sure na hindi ako mauubusan ng A sub n's because there would be infinitely many intervals I sub n's. All right? And each of those I sub n's will contain infinitely many terms of the sequence. So sure ako na laging makakabuo ako makakakuha ako ng isang appropriate element to serve as an element of our subsequence. Tapos yun yung idea kung bakit natin pinipili yung subinterval na may infinitely many na laman na terms ng sequence. Kasi nga kailangan palaki ng palaki yung mga subscripts na pinipili natin. Right? So dapat unbounded yung subscripts dun sa mga elements na pinipili natin para mag-guarantee na kaya ko silang mapili in an increasing order. All right? And I think there we go. Yun yung kukunin kong subsequence, all right? So yung subsequence na yon ay magko-converge dapat kay A by the squeeze theorem. Bakit siya dapat magko-converge kay A? Kasi nga yung mga A sub n sub k natin, they belong to I sub n, all right? Tapos ang I sub n ay C sub n, D sub n. Alam ko to nagko-converge kay A. Alam ko to nagko-converge din kay A. So by the squeeze theorem, that subsequence will converge to A. And again, what is A? A is the intersection of the infinitely many nested intervals. All right? So there you go. We have constructed a convergent subsequence out of a bounded sequence. All right? And the main ingredient here in the proof, actually may dalawa. Pero I think I can reduce it and rephrase the proof without using the squeeze theorem. So the crux of this proof is really the nested interval property. Okay? So yun yung sabi ni Bolzano at ni Weierstrass. Okay? So any questions with that proof? Ito yung mga pinakaayokong proof sa analysis, yung construction. Kasi ang hirap mag-isip ng isang ingenious way on how to provide an example. All right? And I think that's why analysis is harder than other branches of mathematics, at least for me. Kasi halimbawa sa modern algebra, pag alam ko yung definition, alam ko yung mga na-prove na theorems before, I probably can walk through the proof, right? Paunti-unti kaya kong isulat yung proof kasi halos application lang ng definition, application lang ng mga previous theorems. Sa analysis, minsan, or kadalasan, yung mga proofs kailangan mo mag-construct. And that makes it more challenging, all right? Because you really need to squeeze out the creative juices in you. Okay? So any questions about the proof of Bolzano? Okay, so if none, then I'll proceed to the next big theorem. And this is about Kushi sequences, all right? So ano pa yung pwede nating ibigay na property, all right? Or what would be an equivalent property to being convergent, okay? Or an alternative characterization for convergence. And you will see later that being a Kushi sequence is one of those equivalent characterizations, okay? But first, ano ang isang Kushi sequence, all right? Now, a sequence is Kushi if and only for all epsilon greater than 0, there exists a starting index capital N. Kamukhang-kamukha siya ng convergent sequence, right? Pero ito yung pinagkaiba. Such that for all natural numbers M and N greater than or equal to the starting index capital N. So ngayon, meron tayong dalawang sufficiently large indices, namely M and N. Then, kung Cauchy yung sequence, the distance between AN and AM will be less than epsilon. So even though the definition of the Cauchy sequence resembles that of the limit of a sequence, wala itong sinasabi about the limit. Kasi ang sinasabi niya lang, kahit gaano pa kaliit yung epsilon, lagi tayong may makikitang starting index capital N such that beyond that starting index, super magkakalapit na yung mga terms ng sequence. Kasi yung AN at saka yung AM ay within epsilon distance. Alright? So in a nutshell, in a layman's terms, paano nyo i-describe yung pagiging Cauchy? Ganito lang yan. Yung mga terms ng sequence ay palapit ng palapit sa isa't isa habang lumalaki yung subscript. Alright? So pwede mo siyang tingnan, nandito si A1, nandito si A2, pwedeng malayo, nandito si A3. But starting from an index capital N, dapat yung A sub N super lapit na sa A sub N plus 1. Tapos yung A sub N plus 1 super lapit na sa A sub N plus 2 and so on. And all of these guys will cluster around each other, specifically in an epsilon neighborhood. Okay? So yung distansya ng mga malalaki na yung subscript mula sa isa't isa ay mas maliit na sa epsilon. Okay, so that's what it takes to be a Cauchy sequence. And actually, it's not hard to imagine na, kung nagkukumpul-kumpulan sa dulo ng listahan yung mga terms ng sequence o yung mga terms ng sequence sa dulo ng listahan, ibig sabihin, dapat meron yung limit. Yung limit na yon ay naninirahan dun sa epsilon neighborhood. Kasi nagkukumpul-kumpulan na nga silang lahat, so dapat it makes sense that there is a limit in that epsilon neighborhood. Okay, and that's what we will prove in. Actually, yung pala yung converse. Sorry, I'm getting ahead of myself. Nauna pala yung theorem 2.11. Ano yung sinasabi ng theorem 2.11? Every convergence sequence is a Cauchy sequence, which actually kaya ko ring i-explain galing dito sa little example that we have. Kung convergent yung sequence natin, ibig sabihin, yung mga terms ng sequence, after some starting index, ay nagkukumpul-kumpulan na dun sa limit na little a. So all of the terms will live inside an epsilon neighborhood of the limit a. So kung naninirahan sila sa isang epsilon neighborhood, so yung distansya ng mga malalaki na yung subscript mula sa isa't isa ay magiging mas maliit na sa epsilon. Alright? And that's why, excuse me. Sorry, nasamid ako. And that's why we can say for certain na nagkukumpul-kumpulan na yung mga elements ng terms within an epsilon neighborhood in the long run. Okay? Yun yung theorem 2.11. Every convergent sequence is a Cauchy sequence. So it makes sense graphically, but statement. All right? Now, gawa muna tayo ng prelim analysis bago natin isulat yung actual proof. So, ang assumption natin ay convergent yung sequence. All right? So, what do we know about a convergent sequence? Kahit ano pa yung epsilon na piliin natin, merong starting index such that after that starting index, ang distance ng a sub n minus a ay less than epsilon for a unique real number a. Yan yung convergence to the number a. Pero ano yung gusto nating ipakita? We want to show that the sequence is Cauchy. That is, for the same assumption, for all epsilon greater than 0, we should always find a starting index. Ang kaibahan naman nito, dapat yung a sub n minus a sub m ay less than epsilon. Okay? Pero ano yung condition kay little n at saka kay little m? Sila dapat ay sufficiently large. So kung sufficiently large sila, pwede sila makiride dun sa restriction na yung little n dun sa definition ng convergent sequence ay mas malaki dun sa starting index capital N. Alright? Kasi ito rin naman yung kailangan dun sa definition ng pagiging Kushi, right? So I just want to establish this inequality coming from this one. Alright? A sub n at saka A. Now, alam ko na si M at saka si N ay parehas mas malaki na kay capital N. Alright? So that means I need to manipulate this inequality, A sub n minus A, to come up with this guy for sufficiently large N and M. And the usual trick that we learned whenever dealing with inequalities is adding and subtracting the same amount, alright, doon sa loob ng inequality. Alright? Sa loob ng absolute value rather, right? So ano ba yung kulang? Ito yung goal natin, absolute value ng a sub n minus a sub m. Ito yung meron tayo. This will be coming from the assumption that the sequence is convergent. So ang kulang ay walang a sub m. So why not add and subtract a sub m? Alright? And then, usual trick, gamitin yung absolute, triangle inequality, a sub n minus am plus absolute value ng am minus a. Ito yung mga usual trick na dapat pinipick up natin along the way, right? Tapos, pabaligtad pala yung ginagawa ko, no? So, let's see. Feeling ko ang ginagawa ko pala yung converse. Hold on. Ang assumption siya ay convergent. So we know that this is less than epsilon. Alright? Ang gusto nating mapakita, baligtad yung ginagawa ko. Gusto ko to ay less than epsilon, ay maging less than epsilon. So, sorry about that. Converse yung ginagawa ko. Sorry, bakit converse yung nasa isip ko? So ito yung gusto ko mapakita, right? So dito pala ako dapat nag-start. Tapos gagamitin ko tong assumption na to. Mas-spoil tuloy kayo dun sa proof ng converse. Pero anyway, so dito ka ito yung gusto kong ipakita to be less than epsilon and I'm gonna use this one. Alright? Now, para magamit ko to, kasi siya yung nasa assumption, dapat ito magkaroon ng A. So para magkaroon siya ng A, so why not subtract and add A dun sa nasa loob? Yan, I think tama na to. Tapos, triangle inequality. A sub n minus A plus A minus A sub m. Alright? Now, ano yung malalaman natin, ano yung pwede nating i-deduce or ano yung alam na natin about these two terms here? Yung A sub n minus A, si n ay lampas na ng capital N. So, ibig sabihin, this guy will be less than epsilon. Or we can make it to be less than, it's less than epsilon. So, sulat ko na, less than epsilon. Tapos ito, what about A minus A sub m? Well, you can just rearrange the terms. You can write it as am minus A inside an absolute value. But what do we know about little m? Little m is another large subscript. All right? So, lampas na rin siya ng capital N. Dahil lampas na rin siya ng capital N, mag-hold pa rin itong inequality na to. So, this guy will be less than epsilon. So, in total, magiging less than epsilon. Alright? Pero gusto nating mapalabas itong an minus am ay merong absolute value na mas maliit sa epsilon. So, paano maging mas maliit sila sa epsilon? So, gawin ko na lang itong epsilon over 2 at saka epsilon over 2 para mawala yung 2 dun sa harap ng epsilon. And I can do that because the definition of convergence works for all epsilon greater than 0. So if epsilon is greater than 0, epsilon over 2 is still greater than 0. So I can use the definition of convergence kay epsilon over 2. Makakahanap ako ng starting index capital N such that this guy is less than epsilon over 2. Then what I'll do is to select little n and little m to be both greater than or equal to capital N so that this analysis will hold. Okay? So yun yung magiging strategy natin pag, yun yung magiging strategy pag susulat ng actual proof. And actually, to save some time, alright, ipa-flash ko na lang yung proof dito. Actually, yun yung ginawa niya. So, inassume niya na nagko-converge si A yan kay A, ginamit yung definition ng convergence. So, for any epsilon greater than 0, merong starting index such that after that starting index, yung absolute value ng A sub n minus A ay less than epsilon over 2. Alright? So, ito yung nakita natin kanina. Nagka-problema tayo. 2 epsilon yung sum. Gusto ko epsilon lang. So, kaya ko nalaman na gawin ko yung epsilon over 2. Alright? Now, for any n and m that are large enough, how large enough? They should be both larger than capital N para tong inequality na to mag-hold para kay little n at saka kay little m. Alright? Then we can work with this inequality, do the same trick we did in the preliminary analysis, mag-add and subtract tayo ng A, hatiin siya using the triangle inequality, use the fact that both absolute values will be less than epsilon over 2, and voila, we have epsilon as our final step. All right? And that will end the proof. So here we have established na lahat ng convergent sequence ay Kushi. All right? So, any questions? Sorry dun sa mga bubu. All right? Iba yung nasa isip ko. Yung converse lagi yung naisip kong i-prove kagad. Pero I think that's fine unless you have questions. Wala naman? Okay. So if there are none, let's look at one useful result. And I think this is one result that we will need to establish yung pagiging, para establish yung Cauchy Convergence Criterion. Okay. So siya yung lemma 2.1, which is about Cauchy sequences being bounded. Okay. Alam na natin kapag ka siya ay convergent, dapat siya ay Cauchy. Alright? Tapos alam natin na lahat ng convergent sequences dapat ay bounded. So it's nice to ask the question, is a Cauchy sequence bounded? Alright? Hindi ko siya, hindi automatic na kapag ka Cauchy ay bounded. Kasi ang alam lang natin kapag ka, ang napuprove pa lang natin kapag ka siya ay convergent, siya ay bounded. Ang na-prove natin sa Theorem 2.11, kapag ka siya ay convergent, siya ay Cauchy. Alright? Now, it's nice to think about what's the relationship between Cauchy sequences and bounded sequences. And the answer to that, or part of the answer to that, is that every Cauchy sequence is bounded. Okay? And we have the proof over here. Let's try to look at how it was done. Okay? Now, Cauchy sequence, yun yung assumption natin. So, i-suppose natin, for some reasons that we will see later, that epsilon is equal to 1. Dahil yung sequence natin ay Cauchy, ibig sabihin may mag-exist na starting index capital N such that right after capital N, yung absolute value ng AN at minus AM ay magiging less than 1. So, in-apply yung definition ng Cauchy with epsilon equals 1. Alright? Now, I will use the reverse triangle inequality. I start with this, but by the reverse triangle inequality, this guy is greater than or equal to the absolute value of AN minus the absolute value of A sub N. All right? Now, rito ginamit ko yung N equals M na case. All right? So, si little m, inassume ko siya ay si capital N. Okay lang naman yon kasi ang restriction lang naman kay little m ay dapat siya ay greater than or equal kay N. Right? So what does this tell us? This means that with a little manipulation, in particular, I will just add the absolute value of A sub n to both sides of the equation or transposition. So kaya nagkaroon ako dito ng absolute value of A sub capital N plus 1. All right? So ano yung napakita natin dito? Napakita natin na simula kay starting index capital N, yung mga terms ng mga sequence ay may magnitude na mas maliit na kay absolute value of A sub n plus 1. So ibig sabihin, simula kay capital N, lahat na ng mga terms ng sequence na nandito ay bounded above na by a sub n plus 1. So the only question is, para makonclude na bounded yung buong sequence, bounded din kaya yung mga terms na nandun sa kaliwa ni capital N? Alright? And that is easy, and we have seen the same argument before na meron lang namang finite number of terms before capital N. So ihilera natin sila. Tingnan mo si a sub 1, tingnan mo si a sub 2, si a sub 3, si a sub 4, hanggang kay a sub capital N. Tapos, tingnan natin kung sino yung pinakamalaki sa kanila. And we know that the maximum will exist because we are dealing with a finite set. Alright? Lagi nag-exist ang maximum ng isang finite set. Tapos, piliin ko lang kung sino yung mas malaki sa maximum at saka dun sa absolute value ng a sub n plus 1 and call it capital N. And with that choice, I know that capital N will be greater than or equal to the absolute value of all of the a sub n's, thus proving that this Cauchy sequence is bounded. Okay? And the proof. So lahat ng Cauchy sequence ay bounded. And then I think this lemma will be somewhat used in the proof of the Cauchy Convergence Criterion. Ang tawag dito usually CCC, all right? Cauchy Convergence Criterion. Okay, ano ba yung sinasabi ng Cauchy Convergence Criterion? Sabi niya ay a sequence in R converges if and only if it is a Cauchy sequence. So basically, pwede pala nating define ang isang convergent sequence as a Cauchy sequence and vice versa. Because if it is convergent, we have proven that it is already a Cauchy sequence. Then we only have one problem left to show that a Cauchy sequence is always convergent. And I think I spoiled you a little bit on the proof, pero let's go on and see how the proof is formally written. Okay. Now, medyo kakaiba yung proof na ginamit. I think we could have proven this using the analysis that we did before, right? Buti na lang pala, iba yung proof na ginamit ng notes, hindi kayo na-spoil kanina. But I think that could be written into an alternative proof using only the definition of ng pagiging Cauchy. But again, the larger picture here is the equivalence ng mga statements to the completeness action. So that's why the proofs that you see here for these big theorems actually is written to depend on each other. Pero hindi naman necessary na yun lang yung proofs. Yun lang yung pinili na i-present dito sa module or dun sa handout kasi para ma-emphasize yung interconnectedness nitong mga big theorems na ito. Alright? Now, yung forward, I mean, kapag ka siya ay convergent, yung pagpapakita na siya ay Cauchy ay nagawa na natin. That is precisely Theorem 2.11. Tapos, sabi ko nga sa inyo sa math, kapag ka nakapag-prove ka na ng conditional statement, the next question usually that you will ask is, totoo kaya yung converse? Alright? And apparently, the converse of Theorem 2.11 is true. And collectively, 2.11 plus its converse is what we call the Cauchy Convergence Criterion, or CCC. Okay? Tingnan natin yung proof ng converse. So ang assumption, meron tayong Cauchy sequence. Tapos by lemma 2.1, alam na natin yung sequence ay bounded. Kasi yung pagiging Cauchy implies pagiging bounded. Alright? Tapos dahil meron tayong bounded sequence, kaya kong gamitin si Bolzano-Weierstrass Theorem. Alright? Oh, apparently, alternative siguro spelling ng Bolzano yung Bolzano. Right? So kaya ko siguro siya hindi kinorek last time kasi consistent naman siya doon sa lecture notes. But anyway, by the Bolzano-Weierstrass Theorem, CAN, dahil siya ay bounded, magkakaroon siya ng convergent subsequence. And we will assume that that subsequence, all right, will converge to a number A. Right? And then gusto nating ipakita yung Cauchy sequence ay convergent. Pero nagagaranti ni Bolzano-Weierstrass na meron siyang convergent subsequence. Pero alam na natin na meron tayong equivalent statements before that if your sequences or if your sequence is convergent, then lahat ng subsequence niya dapat nagko-converge to the same number. Right? Tapos meron pa tayong divergence criterion na pag nakakita ka ng dalawang subsequence na hindi nagko-converge to the same value, nagiging divergent na yung sequence. Ang gusto nating ipakita rito, yung sequence ay nagko-converge. So ibig sabihin, kung meron siyang convergent subsequence na nagko-converge kay A, it is logical to think that the sequence will converge to A. Kasi nga kung convergent si A yan, dapat magko-converge lahat ng subsequence niya to the same number. Pero inassume na natin na yung convergent subsequence which we know to exist from the Bolzano-Weierstrass Theorem ay nagko-converge kay A. So dapat lamang kung totoo yung theorem, yung parent sequence dapat magko-converge kay A. Yun yung gusto nating ipakita. Tapos dito nagagana yung preliminary analysis na na-spoil ko sa inyo kanina. Now, alam natin yung sequence ay Kushi. So pag pumili tayo ng kahit anong epsilon greater than 0, laging may starting index capital N such that right after that starting index, yung distance mula kay A sub N at saka kay A sub M ay mas maliit na kay epsilon over 2. Okay? Tapos alam natin na yung na si A sub N ay may subsequence na nagko-converge kay A. Alright? Ang gagawin ko ngayon, pipiliin ko si A sub N sub K, or I mean, pipiliin ko yung subscript na N sub K to be something greater than or equal to N. Why will I do that? I'm gonna do that so that we can guarantee na yung inequality na to ay nag-hold. Kasi itong actually, hindi pala ito yung gusto kong gamitin. Pinili ko si A sub N sub K to be large enough, alright, so that this inequality to be true, galing dun sa definition ng convergence ng subsequence. So itong inequality na to nanggaling dun sa fact na yung subsequence ay convergent kay A. So piliin mo lang si N sub K to be large enough so that this is true, and N sub K is also large enough para mas malaki siya dun sa subscript na nakita na natin mula dun sa pagiging Kushi sequence. So basically, pinipili ko lang yung N sub K to be large enough so that it will satisfy two conditions. N sub K will be greater than N that was required dun sa definition ng Kushi, alright? And N sub K is large enough para naman dun sa definition ng convergence ng subsequence kay A. Now, bakit ko yun gustong gawin? Kasi, di ba gusto ko ipakita convergent yung sequence. So I want to show that A sub N minus A is less than epsilon. Kasi ang claim natin, yung limit ay si A. Alright? Tapos ang natutunan natin ay, kaya ko mag-add or subtract para makuha yung desired inequality, right? So what should be something that I should add or subtract? Well, here I took advantage of the fact that we know that there is a convergent subsequence. And we have chosen an element or a term of that convergent subsequence that will have a sufficiently large subscript N sub K for our purpose. All right? So dahil si A sub N sub K ay pinili ko in such a contrived way so that these two inequalities will be true. So what I can do is to split this, or actually to add and subtract A sub N sub K, and split this quantity into the sum of two quantities, which we know by the triangle inequality to be larger than or equal to the original value. All right? Tapos ano yung dahilan kung bakit ganun ko siya in-split? Kasi alam ko yung A sub N minus N sub K ay mas maliit kay epsilon over 2. Bakit? Kasi si N at saka si N sub K ay parehas mas malaki kesa dun sa starting index N dun sa pagiging Kushi. So that means this inequality will apply to this guy, and I get epsilon over 2 as an upper bound. Okay. On the other hand, I know that A sub N sub K minus A is less than epsilon over 2 because again, N sub K was chosen large enough para dun sa starting index naman ng convergence papunta kay A. So dalawang magkaibang inequalities yung pinanggalingan nitong inequality na na-establish natin. So essentially we have epsilon plus epsilon over 2 plus epsilon over 2 So the sum is equal to epsilon. So what we have shown here, for any epsilon greater than 0, we can find a starting index capital N such that if your index N is larger than the big, actually hindi pala si little n yung kailangan nating piliin na starting index. Ito yung starting index na pipiliin ko dun sa definition ng pagiging convergent. Kasi nga dapat yung starting index ay malaki enough para siya ay maging mas malaki dun sa starting index ng pagiging Kushi at starting index ng pagiging convergent ng subsequence. Alright? So, bilugan ko lang yung kailangan ko sa definition ng convergence. So yung epsilon greater than 0, there exists a starting index n sub k such that after that starting index n sub k, a sub n minus a will have absolute value less than epsilon. All right? And that is essentially the very definition of a sub n converging to a. Okay? So this shows na kapag ka meron kang Kushi sequence, automatic na siya ay convergent. And that completes the Cauchy Convergence Criterion, which tells us that the sequence is convergent if and only if it is Cauchy. And in the proof ng pagiging convergent sequence ng isang Cauchy sequence, we relied on the Bolzano-Weierstrass Theorem. Okay? Medyo ano lang siya, medyo tricky, maraming fine details that are needed. Nalito nga ako kung ano yung starting index na kailangan ko kasi nga dalawa nga pala yung starting indices na nag-work dito sa pagiging Cauchy, yung isa naman sa pagiging convergent ng subsequence. But if you will really pay attention to the little details, I think this is kayang-kaya nyo itong i-absorb. Right? Now, let's take a 2-minute break. Para ano naman, para hindi tayo ma-overwhelm ng, I think that's already too much information for one sitting. Pero sayang yung time. Siguro kaya nating tapusin yung discussion. Kamusta naman guys? Ready na ba kayo sa reading break? Ang hirap makarating sa reading break, no? Ang daming kailangan tapusin bago makapagpahinga. Yeah, that's also my problem, ano? Ang dami kong kailangan tapusin bago mag-reading break, and I want to get them out of my plate para wala na akong masyadong gagawin next week. So, hinga muna tayo ng konti, stretching, mini yoga. Okay. And I think after nito, isang topic na lang, compact sets. Tapos meron doon dalawang theorems. All right. And then the big theorem there is the Hiney-Borel theorem. Pero yung Hiney-Borel theorem, ano nga bang gagamitin sa Hiney-Borel theorem? Actually, I forgot what is to be used in the Hiney-Borel theorem. So let's see. Let's discover later when we start writing the proof of the Hiney-Borel theorem. All right. So let's resume. We will close the unit by talking about compact sets. All right. So ano yung ibig sabihin ng pagiging compact ng isang set? And you will see that it is closely related to being sa pagiging closed ng isang set. All right. So there is just something that we need to add sa pagiging closed ng isang set para ma-conclude na siya ay compact. All right. Now, we'll start off with Theorem 13, which tells us that a limit point x of a set A, or actually, let me rephrase that, a point x will be a limit point of a set A if and only if there is some sequence contained in A that is convergent. Okay? So, ito pala yung connection between sa pagiging limit point ng isang set at pagiging limit ng isang sequence. Ang sinasabi ng Theorem 2.13 ang isang number x ay magiging limit point lamang ng isang set A kung at only kung, tinagalog kasi if and only if, makakakita ka ng isang sequence that is properly contained in A na magko-converge kay A. Pero dapat yung mga A sa Ben hindi nag-i-equal kay X. So essentially, there is a point X is a limit point of A if and only if we can find a sequence contained in the set A less the set containing X such that that limit converges to X. And this will require a constructive proof kasi ang idea rito ay kailangan nating mapakita na indeed, okay, sa kahit anong limit point, makakabuo tayo ng isang convergent sequence that will converge to that limit point. Okay? And vice versa. So let's try to write a proof for this kasi marami pa namang oras. So para mabawasan yung mga exercises na kailangan yung gawin. Alright? Okay. So for the proof, let's start in the forward direction. So let's assume that we have a limit point. Sorry, nakikigulo si Alexa. So, kailangan ko mag-assume na may limit point, tapos kailangan ko mag-construct ng isang convergent sequence kay X that is properly contained in A and not all terms, and all of the terms of A of the sequence is not equal to X. All right? So here we will let X be a limit point of A. And we want to show that there exists a sequence that is properly contained in the set A less the set containing X such that A sub n converges to to X. Kailangan tayong makabuo ng isang sequence na ang mga terms ay hindi equal kay X pero nagbe-belong kay A such that the limit of the sequence is equal to X. Yan yung goal natin. Okay. And here we will just play with the definition ng pagiging limit point kasi yun lang naman yung nag-iisang assumption natin dito. So let's play around that. Kung siya ay limit point, then for all epsilon greater than 0, which actually is a nice indication because that's what we need to show convergence papunta kay X, alright? So for all epsilon greater than 0, ano yung sinasabi kung siya ay limit point? Then that means there exists an element y not equal to X such that y is a member of the epsilon neighborhood of X intersection A. Yan yung pagiging limit point, right? Meron pang isang element si A na naninirahan dun sa epsilon neighborhood of X. Yun yung pagiging limit point niya. And we can do this for any epsilon greater than 0. Okay? Now, in particular, this will work for any n. This will work for epsilon equals 1 over n for any natural number n. Kasi mag-work to sa lahat ng epsilon. So mag-work siya kahit yung epsilon kunin ko as 1 over n. So in that particular case, so there exists a real number a sub n not equal to x such that si a sub n ay miyembro ng 1 over n neighborhood ni x intersection A. Right? With a sub n not equal to x. Alright? Kasi ginamit ko lang yung definition ng pagiging limit point. This time, yung epsilon, pinili ko as 1 over n. Alright? Tapos, yung y na ginaguarantee nung definition ng pagiging limit point ay tinawag ko lang a sub n. And again, we can do this for all natural number capital N. Alright? So what do we have here right now? So kapag ka si n ay equal kay 1, si a, merong isang number, tatawagin ko siyang a sub 1, na siya ay nagbe-belong dun sa 1 neighborhood around x. Tapos, pag n ay equal kay 2, meron akong real number y, tawagin ko lang siyang a sub 2, na naninirahan dun sa 1/2 neighborhood ni x. Alright? So essentially here, pag kunelect ako, anong magandang connective na gamitin? So, thus, all right, yan yung mga paboritong words sa mga mathematicians. So, thus, hence, and so on. So thus, pag kinolekta ko yung a sub n's na nakuha natin kanina, guaranteed by x being a limit point, that will be a subset of capital A less the set containing x, all right? Which is kailangan ko para dun sa definition ng dun sa hinihinging convergence sequence dun sa theorem. Right? So one down, okay na yan. May nag-exist na sequence. Ang kailangan na lang nating ipakita yung sequence na yon ay nagko-converge kay x. Alright? So now, how can we do this? Well, we know that given epsilon greater than 0, given a challenge epsilon greater than 0, kailangan kong pumili ng starting index, alright? But I can choose the starting index capital N so that ang 1 over capital N ay mas maliit kay epsilon. The existence of such a capital N is guaranteed by the Archimedean principle. Right? So pag binigyan, ito na yung challenge para mapakita na siya ay nagko-converge kay x. Alright? So pag binigyan tayo ng challenge epsilon greater than 0, pipiliin ko si capital N so that 1 over n will be less than that epsilon. And I know that however small epsilon is, there exists such a natural number n. Yun yung sinabi sa atin ng Archimedean principle. Alright? Now, such that what? Such that for all little n greater than or equal to capital N, we'll have the absolute value of a sub little n minus a, right? Ito ay mas maliit saan? Or actually, minus x dapat kasi x yung limit. Mas maliit siya saan? Well, we know that each of the 1 over n's, all right, bawat isa sa kanila ay element ng 1 over n neighborhood ni x. So yung layo ni a sub n mula kay x ay mas maliit sa epsilon na 1 over n. So we know that this guy is less than 1 over little n, pero we know that little n is greater than or equal to capital N. So yung 1 over n will be less than or equal to 1 over capital N. Pero ano yung 1 over capital N? Yung 1 over capital N is less than epsilon with or due to the choice of n that we specified earlier. And so what we have here is that for any epsilon greater than 0, we have found the starting index capital N, starting from which the distance between a and x is less than epsilon. So therefore, ang napakita natin dito, si a sub n ay nagko-converge kay x. In other words, kung si x ay limit point, then sure tayo na merong isang sequence kay a sub n na never naging term si x na nagko-converge kay x. Alright? And that completes half ng proof ng Theorem 13. Okay? So, any questions with that? Na naman, no, constructive din naman yung proof. But this is a nice constructive proof, right? It's very elegant. And it's really fulfilling pagka nakasulat ka ng mga proof na ganito, no? Kahit hanggang ngayon, pag nakakabuo ako ng mga proof na ganito out of spontaneously, right? Parang nakaka-boost pa rin ang moral, no? Na kaya mo pala mag-construct ng mga ganitong mga proofs. Okay? Now, before we celebrate too much, right, i-prove na natin yung converse. So yung sa converse naman, gusto nating ipakita na kapag meron kang element na x nung set A, kung saan meron nag-exist na sequence na nagko-converge kay x, then automatically x becomes a limit point. All right? So here we will assume that x is an element of A such that there exists a sequence A sub n that is properly contained in the set A less the set containing x such that A sub n converges to to X. And what we want to show here is that X is a limit point of A. Alright? Gusto nating mapakita na si X ay limit point. So ibig sabihin dapat sa kahit anong epsilon greater than 0, dapat makahanap tayo ng isang isang element ng epsilon neighborhood ni X different from X that belongs to mali yung sinabi ko. So gusto natin makakita na gusto nating mapakita na pag bigyan tayo ng kahit anong epsilon greater than 0, makakakita tayo ng element aside from X ng epsilon neighborhood around X intersection A. Yung gusto nating ipakita, right? Pero ang assumption natin dito ay merong sequence A sub n na nagko-converge kay A. So let's use that info, all right? So that means given any epsilon greater than 0, there exists a capital N in N such that whenever N is greater than or equal to capital N, then ang A sub N minus X ay may distance na less than epsilon. Okay? So yan yung sinasabi ng pagiging convergent. But actually, I can translate it a little bit, okay? Pwede kong sabihin na ito or pwede ko itong i-rephrase by saying that A sub n then will be an element of the epsilon neighborhood of X intersection A. Right? Yun yung definition, yun yung makukuha natin mula dun sa inequality na to. Bakit? Because we know that, ano pa yung isa kong alam? A sub n will not be equal to X. Alam ko itong A sub n, hindi lamang nasa epsilon neighborhood ni X, pero nagbe-belong din siya kay A kasi yung A sub n ay subset ng A. Tapos yung A sub n ay hindi magiging equal kay X kasi nga subset yung sequence ng A minus the set containing X. Alright? And so what have we found here? We have found that that the intersection of any epsilon neighborhood of X and A is non-empty, all right? Actually, more than that, it will contain an element of A that is different from X. And that is actually the very definition of X being a limit point of A. And that ends the proof. All right? Medyo ang dami nangyari dun sa proof, no? Okay, questions? Konting tease na lang guys para makapagbakasyon tayo ng Holy Week. Alright, tatapusin ko na lang siya. I think we only have one definition and one theorem left, which is the Hiney-Borel theorem. Okay. Now, i-define na natin yung pagiging compact. Alright? So, kailan nagiging compact ang isang set? Well, definition 2.9 tells us that the set is compact if and only if every sequence in K has a subsequence that converges to a limit that is also in K. So makikita nyo mas stringent kaysa sa pagiging closed. Kasi ang ibig sabihin lang ng pagiging closed, laman niya lahat ng limit points niya. Pero para ikaw ay maging compact, dapat lahat ng sequence kay K, hindi kailangan maging convergent, pero dapat lahat ng sequence ni K, sequence kay K, na may convergent subsequence, dapat magko-converge doon sa isang element ni K. Right? So, consider mo lahat ng sequence kay K. Right? Tapos, hindi mo titingnan kung convergent yung sequence na yon. Pwedeng hindi siya convergent, basta dapat meron siyang convergent subsequence. Tapos titingnan mo yung mga convergent subsequence na yon. Sila ba ay nagko-converge? Pag nag-converge sila at yung limit nila ay na kay K then we can say that the set K is compact. Ang daming kailangan para maging compact, right? It's very stringent than compared to being closed, all right? Pero thanks to Hiney-Borel theorem, bibigyan niya tayo ng isang sufficient and necessary condition for pagiging compact, which is actually much simpler than definition 9. Okay? But before going there, tingnan natin yung example 2.7. Okay? An example of a compact set are all the closed intervals. Bakit lahat ng closed interval ay compact? Alright? Kasi kapag kumuha ka ng isang sequence na nasa loob ng isang closed interval, sure ka kaagad na siya ay bounded. Alright? Tapos dahil bounded siya, so kahit anong sequence na nasa loob ng isang closed interval ay magiging bounded. Alam natin, sorry, kapag meron kang bounded sequence, hold on guys. Okay, alam natin na pag meron kang bounded sequence, by Bolzano-Weierstrass Theorem, lagi siyang merong isang convergent subsequence. So we need to test if that convergent sequence will converge to an element of the closed interval. But we know that the closed interval is a closed set. So lahat ng sequence, basically kailangan ko pala yung Theorem 13. So yung closed interval ay closed set. So ibig sabihin, lahat ng limit points ng closed interval ay nasa loob ng closed interval. Pero kailan ka ba nagiging limit point? Nagiging limit point ka if and only if limit ka ng isang sequence na nandun sa loob ng set. Alright? So yung convergent subsequence na A sub n sub k ay magko-converge sa isang element tawagin nating x. Alright? Pero itong sequence na to, itong subsequence na to ay isang sequence na nasa loob ng closed interval. So pag ginamit natin yung Theorem 13, sasabihin niya na, oh, dapat yung limit ng subsequence ay dapat nasa loob ng set. Alright? So, and then we are sure of that because the closed interval is a closed set. Laman niya lahat ng limit points niya. So, yung limit ng convergent subsequence by Theorem 13 ay dapat isang limit point ng set. Alright? So, ibig sabihin, yung limit x nito ay isang limit point ng closed interval CD. Pero yung closed interval CD ay closed. So, laman niya lahat ng kanyang limit points. So, yung limit ng kahit anong convergent subsequence ng kahit anong sequence sa loob ni CD ay nasa loob pa rin ni CD. And that tells us that any closed interval is compact. And then we will end with the Hiney-Borel theorem. All right? Kasi super hirap nga ng definition ng pagiging compact. The Hiney-Borel theorem usually is an alternative definition. If you will be reading some books, you might see that they define a compact set this way. Tapos theorem nila, etong definition 2.9. And that can be done kasi yung mga if and only if statements, there are characterizations and they can be used as definitions. So pwedeng ito yung definition, ito yung theorem, or in our case, ito yung definition natin, ito yung theorem natin. Okay? So do I still have some time? Siguro kaya pa namang i-prove yung, let's see. If and only if, blah, 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 blah. Okay, now I'll stop here. Masyado nang marami tayong information for today. I'll just give you a link to my proof or my discussion of the proof of the Hiney-Borel theorem from the previous semester. Yung proof niya, gagamitin lang yung pasikot-sikot ng definition ng compactness, alright? Kasi yung forward direction, we will assume that K is compact, and then we will show two things. Siya ay closed at saka bounded. So maglalaro tayo dun sa definition ng compactness para maipakita na siya ay closed. Alright? Probably with the aid of Theorem 2.13. Tapos magpo-proof by contradiction pa ako dun sa boundedness. Ipapakita ko na imposible na maging unbounded yung set K na compact. So that's why it will take a little bit of work. Tapos sa converse naman, let's see, ano yung kailangan sa converse? I-assume ko siya ay closed and bounded. Yeah, direct definition lang ng compactness yung gagamitin ko. So that should be fine. Pero medyo, I think 5 minutes is not enough to do that. All right. So later today or early tomorrow, I'm gonna give you the link dun sa papanoorin nyo para sa discussion on kailan? For Holy Tuesday. Okay. So siguro ilalagay ko na lang siya dun sa homepage natin. Lalagyan ko siya ng meeting, supposedly yung meeting link for Holy Tuesday. Papalitan ko nung link natin para dito sa video na ito. Alright? It's just a little portion of the video, probably 15 to 20 minutes yung proof ng Hiney-Borel theorem. Alam niyo naman ako pag nagpo-prove matagal. Alright? So mahaba yung discussion. So I'll just ask you to watch it. But it will not take you more than half an hour to finish the recording. Okay? Watching the recording. And that would be for Holy Tuesday. So that means, yes, success tayo. Hindi na tayo mag-meet on Holy Week. So after I dismiss you today, we will meet na kailan? April, so yung April 2, okay, April 12. Ang tagal na, April 19 na pala tayo susunod na magkikita-kita. Tama ba? I think so. All right, so do you guys have questions or some clarifications? Ramdam ko yung overload kasi napagod din ako pag-discuss today.
Ano nga ba pong meron po? Ay, sorry po. Sorry.
Sige, go. Go, Michael.
Ano pong meron sa April 14?
Sa April 14? Monday kasi siya. So, hindi tayo magkikita-kita ron. Pero sa 175, magkikita-kita na tayo ng April 4. Sorry. Hindi pala. Sorry. Mali pala yung calendar na tinignan ko. April 14. April 14, Michael, ay Holy Thursday na. Monday, Thursday. So, holiday na yung 14. So, hindi na tayo magkikita-kita na. So, talagang April 19 na yung balik natin. Alright? Kasi ang holiday yata ay 14 and 15. April 14 and 15 due to the Holy Week. So, yeah. Sama na natin na holiday yung 12, Holy Tuesday. Balik tayo ng April 19. Alright? So with that, guys, thank you for joining me today and bearing with me. Tatatlo na kayo natira. Shout out kay Trisha, Michael, and Prince. Congrats for surviving this very long lecture. Hindi naman long, pero very comprehensive lecture. Masyado tayo maraming na cover na topics. So enjoy the rest of the day. Keep safe during the long break. Take some time to relax. Be with your family and friends, or kung kailangan nyo mag-catch up with some of your academic requirements, take advantage of the break. Submission being for the NCOE webinar, I think so, Prince. Ida-double check ko rin. Pero ang deadline nun ay tomorrow, right before midnight. Pero sige, pwede ko sigurong i-extend hanggang... Kaya lang baka mapagalitan ako kasi reading break na. No, I'm gonna stick to April 1. So, submit nyo na bukas kasi hindi ko na siya i-extend. Meron na daw, sabi ni Michael. All right, thank you. So until then, keep safe, guys. And yeah, let's see each other again on April 19. Bye, everyone.
Thank you po, sir.
All right.